Hey, my name is Jackie Cole. I'm a professor in biomedical engineering at NC State University. My lab studies bone biomechanics, and today we're going to look at breaking bones to understand what makes them strong. When we move, our bones experience different types of forces, like tension, compression, bending, torsion or twisting, and shear or sliding. Because bone is alive, it adapts and changes in response to these different forces, making it stronger and more resistant to fracture. As engineers, we use mechanical testing to measure the structural properties of bone under these different types of loading scenarios. And we're interested in the properties of normal, healthy bone, as well as how these properties change with different diseases or injuries. Understanding how bone weakens helps us develop better treatments to prevent bone loss, like with osteoporosis or diabetes or cancer. One of the things that makes bone strong and good at resisting fracture is that it is a composite material. Do you know what a composite is? Composites are things like the body panels in this Lamborghini, made using an epoxy that's been reinforced with carbon fibers. Another example is the concrete in the Hoover Dam, which has cement that has been embedded with gravel and sand. Concrete can also be reinforced with metal rebar, and that's commonly used in bridges and buildings. Fiberglass is commonly used in recreational objects that are light, like boats, kayaks, and surfboards. And it's made using plastic that's been embedded with glass fibers. And even some candy, like these Twizzlers that are filled, can be considered a composite material. Composites are different materials that are combined together to make a better material, one that is better at resisting complex forces in multiple directions, like our bones. Here you can see on the right the composite nature of bone at the nanoscale. It's made up of collagen fibers that are reinforced with mineral crystals. You can think of collagen kind of like the wood in these popsicle sticks, and the mineral is kind of like chalk. Let's see how well these materials hold up with bending forces. This is my trusty assistant, Theo. Hi, Theo.
Hi.
Can you bend the popsicle stick for me?
Sure.
Hold it up and show me. Bend it till it breaks. So what happened?
It was flexible.
Yeah? And then what happened?
And then it broke. Because some woods aren't that strong.
And what do you see where it broke?
Little pieces from the inside, which the popsicle stick is made of.
Now what do you have?
I have chalk.
Okay, do the same thing. Let's bend it. What happened?
It wasn't being flexible because it broke in 1 second. And the other one wasn't like 2 seconds because it was being flexible. This one's not flexible because it did it faster.
And what's it look like?
It looks like a Twizzler but filled in, but if it was red, it would be a Twizzler filled in.
Did it break the same or differently?
Differently.
How?
Because it did it faster and it was like a tube of concrete instead of the little pieces of wood that the popsicle stick's made of.
Thanks. Now let's see how bone does in bending. We have some chicken femurs that we took from the thigh, and we're going to be breaking them and bending using this hand crank mechanical testing system. And as Theo turns that crank, what's going to happen is the upper loading point is going to move down to apply force to the top of the bone and cause it to bend. How do you think the bone is going to break? Do you think it's going to break more like the popsicle stick or more like the chalk?
More like the popsicle stick because it's very flexible because it's strong and it doesn't break as fast.
Oh, that's what you think?
Yeah.
All right, let's find out. Okay, here's our bending test. So what you're going to see during the test is that this upper point is going to slowly move down and bend the bone. And on the right, we have a plot of the force as it's being applied to the bone and the position or distance that the middle of the bone moves downward as it bends. And so now we're going to start the video. And at first, what you're going to see is that the force and position increase linearly as the bone deforms in an elastic manner. And like an elastic band, if we were to remove the force at any point in this linear elastic region, it would go back to its original shape. And now we're going to start to see that the curve is going to become nonlinear. And what's happening here is the bone is beginning to deform permanently, and pretty soon it's not going to be able to withstand as much force. And it's going to keep deforming until it breaks. And there you can see it fractured and broke completely. And at this point, the bone becomes so weak that it can no longer withstand force. And so you can see that in the plot, the force dropped off to 0.
Okay, Theo, we just broke that chicken bone. So what do you think? Was your hypothesis correct?
Yes, because comparing the popsicle stick that broke on this side with the bone, it looks kind of similar because this long piece looks like that, and that little cup is in the same spot as that bone. So my hypothesis was correct.
Great, thanks for your help.
You're welcome.
Let's look at that force position or force displacement plot again. So when engineers test materials like the chicken bone, we use these types of plots to tell us about the structural properties of the material. One common metric is called stiffness. It's the slope of that initial linear or elastic region. And stiffness tells us how much the bone deforms for a particular applied load. So how do you think the slope would change if the bone was stiffer? Exactly, the slope would increase. And so an increase in that slope means the bone is more stiff. And on the other hand, the slope would decrease if the bone was less stiff. So what makes bone stiff and strong, and what makes it flexible? Well, remember that collagen and mineral both contribute to the mechanical behavior of bone. And we know that collagen makes our bones flexible. And you can see here, if we didn't have collagen in our bones, the bone would be stiffer. And so you can see that with the increased slope there. It would still be strong, so you can see it would still be able to withstand high forces, but it would be more brittle, meaning that it would break with little bending or little displacement. And on the other hand, if our bones didn't have mineral, they would be much less stiff, so I have a lower slope here, and they would deform more easily or have a lot of displacement and not be able to carry much force. A normal healthy bone is in between these two extremes. And you can clearly see here the advantage for having bone as a composite material. With both collagen and mineral, bone is very strong without being brittle. Thanks for watching. For more videos about biomechanics, check out our Triangle Biomechanics YouTube channel. You can also find out more about my research lab on our website or on Twitter.
Happy National Biomechanics